My name's Andrew Robertson. I'm a senior research scientist at the International Research Institute for Climate and Society at Columbia University. I'm the leader of the climate group here. Some of my research interests are regional climate variability and predictability, and the tailoring of climate information for use in climate risk management studies and climate change adaptation. This webinar will be a Q&A session on global climate models, the models used for climate forecasting and climate change projections. I'll be addressing some of the ingredients of these models, how they work, what scientists use them for, but also some of the limitations of using these models. I'll also be addressing climate downscaling for obtaining finer scale information from these models. Here's an outline of the main questions that we'll address. The webinar then concludes with a summary wrap-up by Erica Allis. So what are GCMs? GCM stands for Global Climate Model or General Circulation Model. These two definitions are used more or less interchangeably. General circulation models are more precisely the numerical models of the atmosphere and ocean circulations, atmospheric GCMs and ocean GCMs, that are coupled together along with models of other components of the climate system to form a global climate model. More generally, these are also called Earth system models. GCMs simulate the evolution of the Earth's climate system over time, including the atmosphere, oceans, sea ice, land surface conditions, and the biosphere. They describe how these components interact with each other to create Earth's complex climate variability and change. This graphic illustrates the complexity of the factors influencing Earth's climate. GCMs vary in their treatment of these factors and may include only a subset of them, depending on what a particular GCM is being used for. For example, GCMs model how climate is ultimately driven by solar radiation, how it responds to variations in solar input, most basically through the seasons, but also on longer time scales, and how it responds to human influences like greenhouse gas emissions and anthropogenic and natural aerosols like volcanic eruptions and smokestack emissions. We can distinguish three broad types of GCM usage. The first is research of the dynamics of the climate system carried out at university and other research institutes. The second is forecasts, from weather forecasts to seasonal forecasts and even longer term forecasts. And then the third is projections of the impacts of anthropogenic greenhouse gases, called GHGs, and aerosols on future climate over a century or more. Here's an example of a seasonal forecast. It shows regions where there is an enhanced likelihood of drier than normal conditions in the yellow to brown colours and wetter than normal conditions given in the blue colours. The stronger the colour, the higher the likelihood. GCMs provide forecasts globally, but let's zoom in over Africa and unpack this graphic a little. This forecast predicts the climate conditions for the November 2010 to January 2011 three-month season, based on the conditions in the preceding October when the forecast was issued. It answers the question, what are the probabilities of above normal, near normal and below normal precipitation expected to be? For example, it predicts a 50% chance of wetter than normal conditions over South Africa in the green colour, and 50% chance of drier conditions over Somalia in the yellow-orange colour. The white areas on the map are places where the forecast outcome has equal chance of being above normal, near normal or below normal. The pink areas are the desert regions where it rarely rains, so no forecasts are issued there. What's the difference between a climate prediction and a climate projection? Well, a prediction is typically a climate forecast made only a few seasons into the future. Research is trying to extend this in time range to several years in advance. On the other hand, a projection is a climate simulation in which a set of scenarios of possible greenhouse gases and aerosol emissions are incorporated. It attempts to project the evolution of the climate over the next century. The term simulation is the most general term used to describe all outputs of GCMs, often for research purposes. Let's turn now to the scientific basis of GCMs. The atmosphere and ocean are both fluids, and hence their motions can be modelled mathematically from first physical principles. GCMs take an initial snapshot of these fluids and then use the equations of fluid dynamics and thermodynamics to forecast the evolution of the fluid at a future time, say from days to years in advance. Changes in greenhouse gases and atmospheric aerosol concentrations modify the radiation balance and thus the thermodynamical evolution of these fluids. Altitudes in the atmosphere. The output is often viewed as pixel images, where each pixel represents a GCM grid cell. So like a digital camera, some GCMs have higher resolution than others, but typically 1 to 3 degrees. That's 100 to 300 kilometers for climate studies. Atmospheric GCMs used for weather forecasting have higher resolution, such as 10 to 30 kilometers, but they only simulate a few days into the future. Computer capacity prohibits high resolution climate predictions and projections for the moment, and a high resolution does not necessarily equal higher accuracy. Let's compare statistical and dynamical downscaling. The figures show the performance of downscaled seasonal precipitation forecasts made for the Philippines. Each of the circles represents a rain gauge, and red indicates better accuracy of skill of the seasonal forecasts. You can see just by comparing the colors that the statistical method matches the costly dynamical downscaling at most of the locations. Let's talk a bit more about dynamical downscaling of climate change projections. Dynamical downscaling, regional climate models, add small-scale detail like mountain-induced rainfall not seen on the GCM's large grid. However, if the GCM simulation is incorrect, these errors will also infect the regional model's output and might even amplify errors at small scale, garbage in, garbage out. Importantly, the high-resolution output of a regional climate model might appear more realistic, but resolution does not necessarily equal accuracy. Dynamical downscaling of climate change projections should therefore be viewed with great caution. Here's an example of simulated changes in wind speed and sea level pressure from average of 1961 to 1990 to average of 2071 to 2100. These maps were dynamically downscaled using the same regional climate model from two different GCM climate change projections, GCM1 on the top and GCM2 on the bottom. The panels on the left show quite different projected changes in sea level pressure from the two GCMs. The panels on the right show that these translate into strikingly different downscaled changes in wind speed. For example, for downscaled GCM1 on the top, there are large projected increases in wind speed over Scandinavia and large decreases over the Mediterranean. Downscaled GCM2 shows neither of these projected changes. So GCM uncertainty is large in this example and amplified in the downscaled projections of wind speed. How is GCM output used? We can distinguish graphical products, maps showing seasonal forecasts of precipitation categories, for example, or climate change projections like the one in the previous slide. Secondly, quantitative impacts research. GCM outputs are used to drive impacts models to make forecasts tailored to particular decision needs. Note, though, that GCM uncertainties can be obscured in the second case, especially if the researchers are unaware of them, which is often the case. Given the uncertainties in GCM output, how are these managed? Well, seasonal climate and weather forecasts made by GCMs can be validated by comparing the forecasts against observed data. The map on the right shows a skill score used by climatologists called GROC to compare past IRI seasonal forecasts against data, looking at the forecasts made over past years. The green to purple colours show areas where the forecasts have been accurate in the past. Clearly the skill of the forecast is highly geographically dependent, and these regions also vary from season to season. The skill of seasonal forecast tends to be highest in the tropics than in higher latitudes. Skill maps like this should be consulted before using seasonal forecasts. How do we manage the uncertainty in climate change projections? Climate change projections are relatively new, and they cannot be validated against observational past data in the same way as seasonal forecasts can. However, several validation options exist. For example, the GCMs used to make climate change projections are closely related to the ones that are used for shorter-term seasonal forecasts. In some cases, it's even the same model that's used. So by validating the short-term forecasts made by these models, that can increase our confidence in their climate change projections. Also, to some extent, the GCM projected trends over the 20th century can be compared with past observed trends. This second point is illustrated here in this graphic, taken from the IPCC Fourth Assessment Report. The panels show the evolution of temperature globally, as well as over land and ocean separately on the right. The range of GCM simulations of models that include both natural and anthropogenic forcings are shown in the pink range, which quite closely match the observed estimates over the 20th century, which are given by the black line. On the other hand, the agreement with the observations is poor when only natural forcings are included, such as solar variability and volcanic eruptions, and this is shown in the blue range of temperatures. This provides powerful evidence for taking GCM projections of future climate change seriously. In the previous slide, we saw the output of GCMs given in terms of ranges, the pink range and the blue range of changes in temperature. Modern climate prediction systems use an ensemble approach. Multiple GCMs are each run multiple times with slightly different parameters or initial conditions. So the distribution of the results, the spread of the results, enables the likelihood of different outcomes to be calculated precisely. This approach assumes that the GCM ensembles span the gamut of uncertainty in a realistic way. Here's an example of an ensemble of seasonal GCM forecasts of ENSO. This plume forecast is issued every month by the IRI in conjunction with NOAA's Climate Prediction Center. The graphic shows central equatorial Pacific sea surface temperature departures from average, indicating the evolution of ENSO, the El Niño Southern Oscillation. Cold anomalies indicate La Niña conditions and warm ones El Niño. The forecast with 13 different models was started every month from mid-2011 to 2013, and the strands of spaghetti in the plume show the evolution of each GCM's forecast against the observed anomaly given by the black line. You can see that most of the models did quite a good job of capturing the return to near normal conditions in early 2012, but many of them erroneously predicted an El Niño at the end of 2012.
Hello, I'm Erica Allis, and I'm a Senior Staff Associate in the Regional and Sectoral Research Program at the International Research Institute for Climate and Society at Columbia University in New York. At the IRI, I help develop decision support tools to enhance climate-resilient development in various sectors. In my presentation, I'm going to provide a brief wrap-up of the main points covered in Andy's GCM Q&A and step through one example in which decision makers use GCM outputs to enhance the effectiveness of their development resources. The example I will present is the partnership between IRI and the International Federation of Red Cross, Red Crescent Societies. In this example, I will step through the 4 components that contribute to this program's success, these being the development of climate information, the IFRC help desk, which is based at the IRI, internships, and the staff liaison. Emphasis will be placed on the climate information products since that is the topic of this webinar. So what are GCMs? In the preceding presentation, Andy noted that GCMs are numerical models that simulate the circulation between the atmosphere and oceans. GCMs simulate the evolution of the Earth's climate system over time. These models use a recent snapshot of the Earth's climate system consisting of physical information such as sea surface temperature, atmospheric pressure, winds, humidity, etc. These inputs are normally pulled from publicly available data sets. GCMs can produce both short and long-term forecasts. GCMs can also use greenhouse gas and aerosol emission scenarios to project the evolution of climate over the next century. As you may recall from Andy's presentation, there is a distinction between prediction and projection. So how are GCM outputs used? Well, I'm going to step through one example of this in a moment, but essentially GCM outputs can be used to develop maps that show weather or seasonal forecasts of precipitation categories or climate change projections. GCM outputs can also be used to support quantitative impacts research, in which GCMs drive impact models and are used to tailor forecasts to a particular decision. Before using weather and seasonal GCM outputs, decision makers are encouraged to review the model's skill score to see how well the model has performed over a particular area for a given season. It's important that in using longer-term projections that is, that the QA/QC checks that Andy mentioned in his presentation are performed. Downscaling can enhance the resolution of climate information, but it should be noted that model errors can be amplified in this process, and that the dynamical downscaling of climate change projections should be viewed with great caution. Now let's take a look at one example of how GCM outputs are being used by development professionals. It's important to note that the IFRC-IRI partnership is really just one example of how development professionals are using climate information to inform their decision-making. This example illustrates how disaster managers use GCM predictions. In other words, the use of climate change projections is not really covered in this example. The IRI and IFRC partnership formed back in 2007 to address the need to reduce the impact of global weather and climate-related disasters through prevention and preparedness activities, early warning, and also early action. The partnership goal is to support the effective use of weather and climate information to better manage climate risks in order to reduce the loss of life, the number of injuries, and the impacts of disaster. There are four main components to the IRI-IFRC partnership, and all of these contribute to the success of this collaboration. The first is the tailoring of GCM outputs in an easy-to-understand format to better support climate-informed decision-making within the disaster management community. The second component is the IFRC Help Desk that is located at the IRI. This help desk enables disaster managers to submit questions to climate scientists and receive a response within 24 hours. This helps complete the feedback loop between decision makers and the products that IRI has developed to support their decisions. This formal communication channel helps identify topics or language that needs to be clarified, as well as new climate questions of interest that can further support their decision making. This allows for the product to be further refined over time to better meet their needs. The third component is student internships. This component helps facilitate communication between both the field and headquarter offices for IFRC, and also helps broker relationships between the IFRC, the National Met Services, and the IRI. To date, nearly 100 students have contributed to this partnership. And the fourth component is an IFRC staff liaison that's actually based at the IRI. This is a joint position between the IRI and the Red Cross and further supports the dialogue between climate providers and decision makers to continue to refine the decision support tools. Because the purpose of my presentation is to provide a quick example of what it looks like to use GCM outputs in development decision making, I'm going to be a bit unfair and focus on the first component, or the provision of climate information for disaster managers. But I'd like to take a moment to stress the importance of the other three components. It is our experience at the IRI that simply providing climate information is not enough. The preferences of people using the tool are critical for the tool design and refinement over time. The IFRC Help Desk, student internships, and staff liaison are all critical components of this feedback system. And with that caveat, I now step through the process of identifying climate variables of interest to a given decision-making group, the development of the tools, and how these have been used to support decisions with successful results. This slide helps illustrate the importance of identifying climate variables of interest to a given decision-making group to enable the tailoring of GCM outputs to meet the needs of decision makers. The image to the left is a standard forecast product, or a GCM output, that depicts the geographic distribution of total precipitation for the coming week. For disaster managers, unlocking the meaning behind this map is very challenging because flooding relates to exceptionally heavy rainfall events, but this map doesn't really provide us with an indication of unusual rainfall activity. While the dark red colors over the tropics may look alarming, this may actually be well within the range of what one could expect for the summer monsoon season. As a first step in the partnership, the IRI worked with the IFRC disaster managers to identify the climate information they needed to support their decision-making. Through these discussions, disaster managers stated that in order for them to draw the meaningful conclusions about severe weather to enable early action, they would need a product that puts the forecast into historical context and enables them to pinpoint anomalies. The IRI accomplished this by comparing the current 6-day forecast with historical 30-year average for the same 6-day period. Let's take a look at this. This slide illustrates the decision support tool that was developed for disaster managers. We refer to this tool as a map room. This map room shows a comparison between the 6-day total precipitation forecast, or GCM output, and the historical 30-year average precipitation for the same 6-day period. Areas that indicate high likelihood for unusual wet conditions are depicted in dark blue, and disaster managers can quickly see where they may need to focus their efforts. It should be noted that this is actually not the original version of the map room, but rather the culmination of years of feedback and collaboration to define the climate information of interest to this specific group. In this map room, decision makers can select their climate question of interest from the radio options provided, and in the example above, we have selected where is exceptionally heavy rainfall expected. This map room also provides information on early action options. If exceptionally heavy rainfall is expected, humanitarian first responders are advised to 1. Contact their local Met service, 2. Monitor forecasts for at least 6 days, 3. Consider who may be most affected by heavy rainfall, and finally, review contingency plans. As mentioned earlier in Andy's presentation and in my summary of the GCM outputs, model skill is an important factor to take into consideration when using forecast products. There's also a skill map in the IFRC Map Room series that enables disaster managers to quickly see how well the models are predicting seasonal forecasts in an area of interest. In this slide, I want to highlight how the use of climate information in decision-making can contribute to successful results. Back in May 2008, the West Central Africa Zone of the IFRC initiated an emergency appeal based on a seasonal climate forecast, and this was a first. The seasonal forecast which triggered the appeal is shown on the right. If you recall from Andy's presentation, the green shading over West and Central Africa indicate above normal rainfall in the upcoming rainy season, implying above normal flood risk. To respond to this risk, the IFRC took a series of proactive actions to improve flood management and response preparations for the 2008 rainy season. They pre-positioned relief items, they bolstered preparedness through training initiatives, they worked with engineers to schedule controlled dam releases, and they developed flood contingency plans, and they also launched pre-emergency funding requests. Heavy rainfall over the course of July 15th through 27th resulted in flooding over the entire region, and the flood waters remained high from July 29th all the way through August the 10th. An IFRC evaluation of this early action drew a few interesting conclusions. First, the pre-positioning of relief supplies enabled most countries to receive the needed supplies in a matter of days, whereas a previous flooding event, it took over 40 days. They also found that early action saves money. IFRC estimates that the early action measures helped lower the total cost per beneficiary by 33%. Furthermore, lower reliance on the IFRC's Disaster Relief Emergency Fund due to the investments made in advance proved more resource efficient. And the controlled dam releases significantly contributed to the reduction of lives lost. There were back in 2007, 30 plus lives were lost in floods, and only 2 lives were lost in 2008. The trained staff also helped support efficient response, and the newly developed early warning communication system enabled one small community to evacuate just before flooding. There was physical damage, but no loss of life in this area. As a result of Gambia's early training, they were able to perform a post-flood needs assessment and submit a funding request within only 2 days. The IFRC example provides an indication of how GCM outputs can be used to help disaster managers anticipate and manage climate risks to effectively respond to disasters. This concludes my wrap-up presentation. In closing, I want to reiterate that the IFRC-IRI partnership is only one example of how decision makers can use GCM outputs. The climate variables of interest within your portfolio of development activities will likely differ between stakeholders, and the climate information and decision support tools should be tailored accordingly. As shown in the case example, disaster response professionals are often interested in climate extremes or the chance of above or below normal rainfall conditions. Farmers, on the other hand, may be more interested in the start date of the monsoon rains or the likelihood of consecutive dry days in a critical growing period. Policymakers may be interested in climate change projections when evaluating long-term infrastructure investments and energy policy. Consultations to understand the decision context and the climate information required is an important first step. This concludes the GCM webinar and wrap-up. I hope the webinar has helped advance your understanding of GCMs and how you might use this information in your development activities.